Hello all. I wasn't planning on making a video today, but I was inspired by an experience I had. I was invited to participate at let's say, a family physics Olympiad, which involved, solving kind of practical problems creatively, and you had to compete with other teams, etc. So I competed with a student who is my cousin's daughter, and we won. So, and I kind of miss being around students, because I haven't formally taught in a while. So I decided to make this video where, okay, as you can see in the video, sorry, in the title, we're going to talk about energy. This is from the edXL AS level, advanced subsidiary level, and I guess it's useful to year 12 students, but also to year 13 students who need to refresh their mind about energy and this kind of concepts. Okay, so what else? It's probably useful. Okay, I mean, this is the international edXL curriculum, but I guess it's also useful to UK students. I mean, I think it's the same, almost the same curriculum. So anyway, let's talk a little bit about energy. So first of all, energy is a scalar. Okay. Oh, I forgot to say that I'm gonna keep talking until I run out of notes. So I will have to prepare new notes for new topics I might talk about. So let's start talking about energy. So let's define what is work. Oops. Again, I have to make an effort to write to have a better handwriting. So what is work? Let's start by defining what work is, and then we will get to energy. Okay, so work is the amount of energy, okay, the amount of energy an external force, okay, needs to transfer to an object, okay. So in order for the object, I guess, for the object to move by some distance, okay, or by some displacement, okay, that's another way to say it. Okay, work and in extension energy is a scalar quantity. Okay, so it's the same as the mass. Okay, I mean, all that matters is how how heavy an object is. I mean, what the mass is. It doesn't have a direction, right? Same with energy, work, kinetic energy, gravitational energy. All these quantities are scalar quantities. Okay, they only have a magnitude and units. Okay, and for work, and energy, and any kind of energy, we use joules. Okay. Now, some of you might protest and say, okay, but how? Okay, in this definition, you see that we include the notion of, where is it? I'm looking for, okay, by some distance. So in this definition of work and energy, we have the notion of an object moving by a distance. But some of you might protest and say, okay, we have chemical energy. You know, I burn gasoline, for example, and it burns and it has energy, right? And the same with electrical energy and other forms of energy. So it was proven back in, this, I'm doing this on the fly because it's not on my notes, and I just realized it's important for students to know. It was proven at some point, I think about 200 years ago, when people were working on thermodynamics, it was proven that mechanical energy and thermal energy are equivalent, meaning that if I use 100 joules of thermal energy and 100 joules of mechanical energy, I will have the same result on something I want to do, maybe moving an object, because eventually thermal energy is used in machines, and machines transfer energy to wheels, for example, and the car moves, okay? So it was proven that all forms of energy are equivalent. So when we say 100 joules, okay, 100 joules of mechanical energy will have the same effect on a car as 100 joules of thermal energy, 100 joules of chemical energy, 100 joules of electrical energy, 100 joules of gravitational energy, if that's possible. I mean, I cannot picture how you can pull a car with 100 joules of gravitational energy. Maybe you can use a planet and pull it. I'm joking, okay? But the main point here is that all forms of energy are equivalent, okay? Now, let's move on. We haven't mathematically defined what work is, okay? So let's do that. So the change in work done is equal by the force applied on an object times delta S, okay? Where delta S is the displacement, okay? So this thing is the displacement, okay? And we can also write this as F times delta S only if F and delta S are in the same direction, okay? In the same direction. Okay. Is there anything else I want to say here? Okay, we already said that this is a scalar. Okay, let's write it again. And let's move on. Okay. Important. This is something that you don't really learn in high school, okay? This is called the dot product. Those of you who take algebra or math, advanced math, maybe, I don't know, I should check. I can also teach math at the A levels probably if I look at the material, because my very initial studies were in applied math and applied physics, so I know enough to teach high school at least. So this is called the dot product, okay? I don't know where it's taught in math, but it involves this notion, okay? I'm gonna write it and then erase it because it's not something you need to know. But if you have a force in this direction, okay, and the object moves in this direction, okay, and there is an angle theta between these two quantities, then F, this is called dot, okay, this is the dot product. So F dot delta S is equal to F, the magnitude of F, okay, times the magnitude of the delta S, times the cosine of the angle between them, which is theta, okay? But you don't learn it this way in high school. So I'm gonna proceed with discussing cases, okay? I think it's more proper for high school students. So cases. First case, F and delta S are parallel, okay? And in the same direction, Okay, so the case is the following. So maybe there is a floor. Actually, let me use a different color for the floor. Let's use green because we are out in nature maybe. So let's see, let me use this new feature of GoodNotes. Yes, okay, if I keep the pen pressed on the screen, it makes it straight, which is great. Okay, so let's draw a box. Okay, so there's a box and I apply force F, and the object moves, the box moves by some displacement delta S, okay? Then the work done, in this case, is F times delta S, okay? Simple. Let's do the second case. F and delta S are parallel, but in opposite directions. But in opposite directions. Okay, let's use the green again. Okay, it didn't make it straight. Let's try again. If at first you don't succeed, always try again, guys. Okay, great. So maybe the case now is the following. We have the same box as before. Okay, it moves by the same displacement, delta S. Okay, so this is delta S. But there is a force acting in this direction on the box. But it nevertheless moves to the right. So how is this possible? Okay, in reality, there is a resultant force to the right. Okay, and in reality, I mean, in real life, this force that points to the left will be friction, might be wind resistance, something like that. But in any case, this force does negative work. So W is minus F times delta S, okay? And this is common. I mean, the most common cases in high school are friction and drag force, okay? Drag force from air or a liquid, okay? A fluid in general, okay? Another case that is important to know, and students get it wrong very frequently, more frequently than you would hope. So F and delta S are perpendicular, okay? Those of you who do take advanced math, or maybe they like math or whatever, they know that since if you go back to the very definition, to the initial definition over here in the blue box, since this is a dot product, okay, if two vectors are perpendicular to each other, the dot product is always 0, okay? So this is the case we will discuss. So again, I made a mistake. Okay, so okay, great. So maybe I have a box, the same box as before, okay? And somehow it moved to the right by some distance, delta S. Okay, so that's delta S. But during this motion, okay, there was a force F pointing upwards, okay? And this force is perpendicular to the box, okay? So in this case, the work is 0. The work is 0. F does no work. And the same is true for weight, okay? So the weight points down, right? So the work done by the weight is also 0, okay? So I'm going to write this in parentheses. So example, weight, but only if weight is perpendicular. I'm gonna write it like that. Is perpendicular to the force, to the displacement, to delta S, to the displacement. Oops. What did I do? Okay. To the displacement. Okay. Displacement delta S. Okay. Great. Okay, do I have any more cases here? Yes, of course. We forgot the most important case. This is the fourth case, which we will call general case. General case. F and delta S make an angle theta. Okay, so again, let's draw the floor. Okay. Okay, our box again moved by some distance delta S. And this is the force. This is the angle theta. So F cosine theta, okay, F cos. Wait, I'm writing without talking. I'm sorry. So let's say that the force is applied to the box, making an angle theta with the horizontal. Then we can analyze the force into a horizontal component, F cosine theta, and a vertical component, F sine theta. And for those of you who are not watching my videos, the rule I use is that the component that touches the angle theta is always the cosine theta, and the component that does not touch the angle theta is the F sine theta, okay? So this component here does not touch the angle theta, okay? I mean physically touching, this is what I mean. All right, so the work done is F cosine theta times delta S, right? Because F cosine theta and delta S are parallel to each other. But we also have, theoretically, we have the work done by by the perpendicular component is 0. So the work done from F sine theta. But I don't want to confuse you, so I'm going to erase this, okay? So when a force makes an angle theta with the displacement, we always use F cosine theta delta S. And if an Excel or any other spec wants to throw you off, they might give you a scenario like this, okay? So here is the box, here is the displacement delta S, here is the force F, this is theta. Using that angle defeated the purpose of making this extra case. So maybe they give you this angle. Okay, let's call it phi. Okay. Now the work done is gonna be F sine phi delta S. Why? Because this component is F sine phi, and this component is F cosine phi. And now F cosine phi is perpendicular to the displacement, therefore the work done by that component is 0. But the work done by the horizontal component is now F sine phi delta S. Okay? What else do I have here in my notes? Let me see. These notes are kind of old. No, they are not. I prepared them kind of recently. Okay, so I want to talk about some situations that can also throw you off. Okay, so I'm gonna write this. Let's title these two examples as careful. Okay, careful for situations as the following. So okay, let's maybe we have an inclined plane. This is really nice, this new feature that GoodNotes added. And they don't sponsor me. If anyone from GoodNotes is watching these videos, please sponsor me. I'm using your software, it's really great. And yeah, and I really liked this update that you made. Or maybe this feature was there all along and I wasn't aware of it. So anyway, so this is an inclined plane, okay? And maybe we have a box, okay? And maybe they tell us that the force is parallel to the inclined plane. So F is parallel to this kind of thing here means parallel, okay? Excuse me. F is parallel to the inclined plane, okay, and maybe the box moved by some distance delta S. Okay, now the work done is what? Can you guess? Pause the video, think about it, and tell me what the work done by this force F is. Okay, I hope you found it, but the answer is F times delta S. Why? Because delta S is a displacement that I didn't draw it explicitly before, But delta S is this vector, right? It's the vector that connects the initial and final position of the object, okay? So in this case, F and delta S are parallel, okay? So the work done is F delta S. Theta is there to throw you off. It's not participating in this problem, okay? So be careful. Okay, that's one scenario. And let's go see another one. So let's draw the inclined plane again, okay? So, okay, let's do this and this. Okay, now I have my incline. And maybe I have a box up here, okay? And it moved all the way down here, okay? So delta S is that. And how did it move? Because of gravity, okay? So m times g is the weight of this object, okay? So we have to analyze this vector, the weight vector, into horizontal and a vertical component. Horizontal to what? The motion, right? So the inclined plane. So we need a component like this and a component like this. Okay, which angle is theta? Is it this one or is it this one? Pause the video and try to figure it out before I tell you the answer, okay? So I hope you found it, but the angle theta is, actually I'm gonna use green. This is the angle theta. And the reason is because this side is perpendicular to this side, okay? And then this side is perpendicular to this side, okay? So this angle is equal to that angle, okay? I hope that makes sense. So therefore, this component is m times g times cosine theta, okay? And this component is mg sine theta, okay? The work done by this force is 0. Why? Because this component is perpendicular to delta S. Now the work done by this component is, can you guess? Pause the video again and try to think of the answer, okay? So this component is actually minus mg sine theta delta S. Plus mg, I'm sorry, because the displacement is, okay, I'm sorry if I confused you, but the box moves from this initial position to this final position. In my notes, I put a minus sign. I don't know why. I guess I was thinking that you actually move the box from down here, the final position, to the initial position, in which case you will need a minus sign. But here we assume that we start up here and ended up down here, in which case delta S is this vector and it's in the same direction as mg sine theta. So therefore, plus mg sine theta times delta S is the answer. All right, so what else do I have here for you? I also have some notes about power and momentum, so I'm gonna try to keep going. I will not cover momentum in this video. I guess I'm gonna make another video. So let's talk about the kinetic energy, okay? So this is the work done, okay? And this definition about the work is a general definition, okay? It applies to any kind of force, okay? Now, as you will see, the kinetic energy is a special type of, let's say, force, okay? I mean, you will see why. And then the gravitational potential energy that you are all familiar with is also another type of force. It's actually the work done by gravity. You will see how. And yeah, let's dive in. Let's talk about kinetic energy now. Okay, kinetic energy. Okay, the kinetic energy, as you probably learned since kindergarten, is 1/2 mv squared. But why? Okay, so let's say that we have a box like before. I don't know why I keep using boxes. So let's use the box example. Okay, so we have a box and we apply some force F on the box. And this box was initially addressed, therefore its initial velocity u is 0. And I'm using u because I'm thinking I have Suvat equations. I have the Suvat equations in my head right now, okay? So let's say the box, force F was applied to this box. And because of this force, an acceleration is building up, right? Due to F equals ma, Newton's second law, right? So if the box moves by some distance, which we will now call s, because again, please think of the Suvat equations, okay, in your head. Because of this force, which we keep applying on the box now has a final velocity v, right? So the work done by this force is F times delta S, right? But what is F? F is ma, right? And what is delta S? It's simply S, right? Because the displacement is by this distance S, okay? But recall that, and I'm going to write in parentheses Suvat, okay? Recall that v squared, the final velocity squared, is equal to u squared plus 2as, right? Therefore, as, and the initial velocity is 0. Okay, so as is v squared over 2. Okay, so if we use this equation, equation 1, equation 2, we see immediately that, so the work done by that force is equal to the kinetic energy, and it's equal to ma times s, but this as is v squared over 2, so 1/2 mv squared. And we recover the equation that is very familiar to people since, again, since kindergarten, right, for the kinetic energy. So, magic, right? So, let's talk about the gravitational potential energy now, okay? So, it's actually easier. I mean, the concept is easier. So, let's talk about the gravitational potential energy. So again, the gravitational potential energy is mgh. Again, you learn this in kindergarten, okay? So, but why? How can we derive it? Again, everything can be derived from first principles in physics. And the first principle here is the definition of work, which tells you a force times a displacement gives you energy, okay? So what kind of force? So let's say that we have a floor, okay? And we have a box on the floor, and we have a box up here, okay? What's gonna happen to the box is gonna fall on the floor. What's the weight of the box? M times G. And what's delta S? H, the height, right? So the work done, since the initial position is here, so this is the initial position and this is the final position, right? So delta S points in this direction, in the same direction as the weight. So the work done, which is equal to the GP, the gravitational potential energy, is again F delta S. What is F? M times G. What is delta S? H. And that's the gravitational potential energy. And for those of you who are going to keep going and learn and move to the A level, I mean in year 13, you will learn that this is true only on the near the surface of the Earth. So I'm going to write it there. I'm going to write it in parentheses. MGH only applies if H is small compared to the radius of the Earth. Okay. If you want to dive deeper into this, G is defined as G times the mass of the Earth over the radius, over the distance. Over the radius of the Earth squared, okay? So G is 9.81 meters per second squared only on the surface of the Earth or near it. I'm trying to say that on the moon, the gravitational attraction from the Earth is not the same as the gravitational attraction from the Earth you feel here on the surface of Earth, okay? So I'm gonna rate this because you don't need to know this. You're gonna learn this in unit, let me think, 4, I think, or maybe it's 5. I'm not sure. I forgot right now. So anyway, derive the kinetic energy and the gravitational energy. So let's move on. Let's talk about the conservation of energy. Conservation of energy. So the gravitational potential energy and the kinetic energy are interrelated. Okay. GP loss is converted to kinetic energy, okay, and vice versa. Okay, so let's set them equal to each other and see what kind of things we can derive. So GP, so we said a loss in GP is converted to kinetic energy. Therefore, mgh is equal to 1/2 mv squared, okay? The mass cancels. So V is the square root of 2gh. So where is this used? For example, if you jump from an aeroplane, okay, let's say that there is an aeroplane up here, okay, so that's an aeroplane. It looks more like a cross. I'm not implying that you're gonna die or something, but anyway, so let's say that someone jumps, okay, this height is h, and someone jumps, okay, or you drop something, maybe you hate someone and you drop them something, I don't know. So if you drop something, then the velocity that object, and it doesn't matter what kind of mass it has, whatever you drop, okay, it wouldn't matter if the Earth had no air, but because of air resistance, it does matter, okay, but that's a different story. In theory, the velocity an object will have when it reaches the ground will be the square root of 2g times the height, okay. That's that. In general, energy cannot be created or destroyed. Oops. Okay. It can only be converted from one form into another. Okay. Some of you will protest and say, when you have friction, energy is lost. No, it's not lost. Okay, so let's do a note here. Note, in the case of friction, okay, energy is lost to heat. And the same is true for sound. Okay. I mean, when sound, when you, I don't know, a collision occurs between two cars and you hear a sound, that sound is energy loss to heat. Okay. Okay. Next, we're going to talk about power. Okay. Which is also another scalar quantity. So let's talk about it. Power. So power expresses how fast energy is transferred, and it's also a scalar quantity. So for those of you who are into electric cars, I'm not. They usually, or Formula E or stuff like that, usually those engines are classified by kilowatts of output. I think it's kilowatts. I'm not entirely sure, but something like that. So the higher the kilowatts, the faster the transfer of energy is to the car. Okay, so you want that number to be as high as possible. So let's define it. So power is work per time. Okay, and it's also equal to energy per time. Okay, because work and energy are equivalent, remember? So and it's measured in watts. Okay, so 1 watt is 1 joule per second. Okay, so is there anything else? There is one more thing I want to tell you, that it's not in the mark scheme. It's not the mark scheme, I'm sorry. It's not in the back of your paper, if I'm not mistaken, but it's good to know. What I'm about to say is good to know for exam taking. So recall that work is F times delta S, right? Actually, let me move this down here. Okay, so work per time, let's call it delta T, work per time, is equal to F times delta S over delta T. But what is this? What is this, guys? Pause the video and think about it. Okay. Okay, work per time is power, and delta S over delta T is speed. So power is also equal to force times speed. Okay. And that's it. I mean, there is nothing more to say. I mean, I think in one of the past papers I solved, I haven't solved enough papers on Unit 1 or Unit 2 yet, but I'm working on it. So it's, I cannot think of an example to use. So I'm gonna move on to defining efficiency, okay? Efficiency. Those of you who are gonna study engineering, for those of you who are gonna study engineering, efficiency is one of the most important concepts you will learn in your lives, probably, because it's highly relevant to making machines, making buildings, and stuff like that. So in a closed system, and a closed system is a system that doesn't interact with external forces, energies, or whatever. We have the following. So in a closed system, maybe we give this system some power or energy. So power or energy in, okay, and we get out useful power or energy. So useful power or energy out, but we also have losses. So this is friction, heat, sound, and so on. Okay, so the total power, or energy in is equal to the total power or energy out. Okay, So what I'm trying to say is that we provide some power or some energy to a machine, and we get some useful power or some useful energy out. So for example, what's this useful energy? So maybe we provide an engine with 100 joules of energy, and the useful energy we get out is the car moving by 10 meters, okay? But the car moving by 10 meters requires 90 joules, maybe, okay? I'm just giving you a crude example. Where did the 10 joules go? They were lost to friction of the tires with the road, friction inside the engine, sound losses, heat losses, and so on. Okay, so we define efficiency as this quantity, okay, the useful power or energy in over let's use green, over the power or energy in, okay, and times, I almost forgot, times 100%. Okay, so this is the definition of efficiency. In an ideal world, efficiency will be 100%. So in an ideal world, E, okay, efficiency would be 100%. But this is not possible, okay? In reality, the efficiency is always less than 100%. Or efficiency is less than 1, because sometimes you measure it using 1, sometimes using percentage, okay? So for example, a usual value for efficiency might be 0.8, which is the same as 100%. Because I remind you that 100% is 8 by 10, which is 0.8. So 0.8 and 100% is the same thing. Okay. Let's do some examples, I guess, and then call it a day. So examples. A machine burns gas. So a machine burns gas to deliver power. I think I already said this example, but anyway. But some of this power is lost to heat. Okay. So in this case, in this example, petrol or gas is the power in, okay, and the useful work is the kinetic energy we get out of this system, okay. Another example might be a light bulb, okay. So in this case, the electrical energy is the power in, okay. The useful energy is the light output, and the waste is heat. I mean, if you touch a light bulb, you will see that it's hot, right? And dangerous to touch sometimes. So anyway, there is one more thing left to close up the mechanics chapter for Unit 1, but I'm not going to do it in this video because it's getting late here and I have something else to do, and I don't want to introduce a new concept in this video. So this is it. I mean, for energy, kinetic energy, gravitational energy, and power, I hope these videos are useful. Let me know what you think. Give these videos likes. Please tell your friends to subscribe if you find them useful. If you find them incomprehensible or have some comments, please give me some feedback. It's always useful. This channel can use some support. Any kind of support is good. And hope to see you in the next video. And this is it. See you guys.